So let us continue with the concept of discrete stage analysis in chromatography. So what does discrete stage analysis do? The column is divided into several ideal stages or units, and each unit is considered to be totally mixed of fixed volume. So the solution or the mobile phase flows, and each unit has certain amount of stationary phase, and the solute is in equilibrium, the solute that is present in the stationary phase as well as the solute that is present in the mobile phase are in equilibrium. So how did we do the solution for this type of system? We looked at the mass balance of the solute entering and the solute leaving, and then we equated that to the accumulation of the solute. Now the solute gets accumulated in two places, one place is in the stationary phase and the other place is in the continuous phase. So the accumulation is equated to amount of solute entering each stage minus amount of solute leaving each stage, that is all, so simple. So you just have a mass balance, and then after that we assumed a linear adsorption type of isotherm. That means the Q, that is the amount of solute that is adsorbed in the stationary phase, is in equilibrium with the solute that is present in the continuous phase in a linear manner. So Q is equal to Kc, that is what we assumed actually. When you do that, we end up with this type of differential equation. Although this equation looks very complicated, but it is not so actually. No? This Q into Cn minus 1, that is the solute entering the stage n from stage n minus 1, and Q into Cn is the amount of solute leaving the stage n. This is equated to whatever is getting accumulated. Now there are two terms for accumulation, one is the solute accumulated in the continuous phase, that is the mobile phase, the other one is the solute accumulated in the stationary phase or fixed phase. So whatever is getting accumulated in the fixed phase we call it Q, whatever is getting accumulated in the mobile phase we call it C. One interesting point you need to note, that the concentration of the solute inside the stage n is same as the concentration of the solute leaving the stage n, that is why here we have put Cn as well as here we have put Cn, so please note that. So in ideal stage process we assume when there is an equilibrium between two streams or phases, the concentration leaving is same as whatever is the concentration inside the stage. So by doing that we end up with this type of differential difference equation. This is difference, this is differential equation. Now here epsilon is the void fraction, Vs is the volume of a single stage. So the assumption is V is the volume of the entire chromatographic column, V by N, N is the total number of stages, that is equal to Vs. Okay. So epsilon is the volume fraction of the liquid, so 1 minus epsilon will be the volume fraction of the solid. So 1 minus epsilon into Vs will give you the total volume of the solid, and epsilon into Vs will give you the total volume of the liquid. So now we introduce the equilibrium, if you assume linear adsorption equilibrium, that means there is a linear relationship between Cn and Qn, then life becomes very simple. Okay. So if we assume Qn equal to K Cn, so please note that the concentration of the solute in a particular stage in the stationary phase and the concentration of the solute in that same stage in the mobile phase are in equilibrium. So Qn is equal to Kcn, Qn minus 1 will be equal to Kcn minus 1, Qn minus 2 will be equal to Kcn minus 2, so like that actually. So the main another assumption is that K is independent of the concentration, that means we assume same K irrespective of the concentrations of the solute in the stationary or in the mobile phase. So when you do that we end up with a much simpler looking equation. Once again this is the mass balance, the amount of solute entering, amount of solute leaving is equal to the accumulation. So this is again called a differential difference equation. You have the difference here, we have the differential equation here. Now you have the initial conditions. That means at time less than 0 there is no solute at all present, the column has only assumed only the mobile phase, there is no solute flowing. So all the stages will have concentration of the solute equal to 0, okay, stage 1 to stage n. Now the solute is injected at time equal to 0, that is C is equal to Cf, then what happens, that is the initial condition. So by using that we can solve the differential difference equation to end up with a relation like this, Cn equal to Cf multiplied by phi raised to the power n minus 1 E minus n divided by n minus 1 factorial, okay, where phi is given by this particular term, Q is the flow rate of the mobile phase, V is the overall volume, n is the number of stages, epsilon is your porosity, K is your linear adsorption isotherm term. So concentration at any stage of the solute in the mobile phase or of the solute leaving that stage can be calculated by this relationship. So this is very useful relationship because we can make use of this relationship with the relationship we have for a normally distributed Gaussian distributed curve that is leaving the chromatographic column, okay. So before doing that let us look at the effect of the number of stages. When n is very large then obviously the distribution reaches a Gaussian type of distribution, whereas if number of stages are very small, for example if n is 1 that means we assume the entire chromatographic column as one single mixed stage, then obviously it is like a stirred tank vessel, then the concentration will fall down as a function of time. So here the x axis is the time, so the concentration will fall down as a function of time when number of stages is equal to 1. So as we keep increasing the number of stages, the shape of the curve initially may appear like this and slowly it will reach a normally distributed shape like this. So for a very large n this is called a Gaussian distribution or a normal distribution, and the equation for a Gaussian distribution, if you remember long time back we introduced it, it is called C is equal to C naught exponent minus T by T naught minus 1 whole square divided by 2 sigma square. Now here C naught will be the maximum concentration it is reaching when the solute concentration leaves the chromatographic column, T naught is your retention time, that is this time, and T naught sigma is the standard deviation of this Gaussian distribution or normal distribution. So this is how a normal distribution equation will look like. Now we can bring in the analysis which we did for a discrete stage model where we assumed the chromatographic column is divided into n stages and each stage is a well mixed system. By doing that we can end up with some very interesting equations. Sigma square will be equal to 1 by n, n is the number of theoretical stages or theoretical plates, C naught is equal to Cf divided by square root of 2 pi n, and T naught is also related to epsilon and k in this fashion actually, and by substituting all the terms we end up a equation for C, that is the concentration profile of the solute as it leaves the chromatographic column as a function of time is given like this, where n is the number of theoretical stages, Cf is your feed concentration, T naught is your retention time. Just like time we can also have a V coming into the picture where V naught is the retention volume. So analogous to this equation we can have another equation exactly similar looking, instead of T by T naught we replace it by V by V naught. So these equations are very useful. So if I have a column, I want to know how many theoretical stages are there in the column, all I do is I inject a sample and I look at the retention time of the peak leaving the column and I look at the spread or the standard deviation and I can tell what is the number of theoretical plates in the column. In fact vendors when they sell the chromatographic column they mention how many theoretical plates does this particular column have. So a larger the number of theoretical plates, you know the column is very efficient in separating, smaller the number, the column is not as efficient relatively. So when we buy a chromatographic column, we always look for the number of theoretical plates and then make a decision on how good the separation efficiency of the column is or not as good, and so on actually. So we looked at few problems in the previous lecture on how to make use of these equations to calculate the number of theoretical plates or stages if I know the standard deviation of my normal distributed curve, or as well as the retention time. Okay, now let us keep doing some more problems so that these concepts become very clear. Now imagine I am using a chromatographic column to purify BSA, bovine serum albumin protein. Okay, so when I use that, now the column is about 80 liters, it is a packed column of 80 liters with a void fraction of 0.4. Okay, so it has got a void fraction of 0.4, that means 1 minus 0.4 will be the amount of solids present inside. Now this particular peak comes at a retention volume of 470 liters. Okay, as I said, just like retention time, we can also call it retention volume. So this maximum happens at 470 liters. Now calculate the equilibrium constant. So if you remember the equation which relates equilibrium constant, the voidage, the column size as well as the retention volume. Okay, this is the equation. T naught, that is the retention time, is equal to epsilon, that is the voidage, K is your equilibrium constant, V is the volume of the column, and Q is the flow rate. So T naught into Q will give you the retention volume, which is 470, and 0.4 is the epsilon, 80 is the volume of the column. So all you need to do is calculate K, the equilibrium constant. So it is very straightforward. Okay, so same equation. So if I take the Q here, Q into T naught is equal to epsilon plus 1 minus epsilon K into V, and T naught Q is the volume of eluate or volume of solute at which the peak occurs. Okay, so by substituting this 470 epsilon equal to 0.4, 1 minus epsilon will be 1 minus 0.4, volume will be 80 liter, I get K as 9.1. So this K is nothing but the linear adsorption isotherm constant, which relates the concentration of the solute in the stationary phase as against the concentration of the solute in the mobile phase. If you remember, Q equal to K into C, where Q is the concentration of the solute in the stationary phase and C is the concentration of the solute in the mobile phase. So very useful data to have. So you get an idea about the thermodynamics of the solute interaction with the stationary phase and the mobile phase by just doing an injection and collecting certain amount of liquid and look at the retention time. Now let us go forward, let us look at another problem, same problem but an extension. Now the maximum concentration is 3.6% of that originally in the column. Okay, so calculate the number of theoretical stages. Last time we looked at different ways of calculating theoretical stages based on the retention time and standard deviation, based on the retention time and width at half maximum. Now this is third approach by which we can calculate the number of theoretical stages. This is we know that the maximum concentration is 3.6% of that originally in the column. Now we want to calculate the number of theoretical stages. So which equation do we use? If you remember, there is an equation relating C naught with Cf, that is the whatever is there in the original. Okay, C naught is equal to Cf divided by square root of 2 pi n. So C naught by Cf is 0.036. So from there we have to calculate the n, that is the number of theoretical, straightforward. N comes out to be 122, very interesting. So we can use this type of approach to calculate the number of theoretical stages. So you see, if the number of theoretical stages are very large, because it comes in the denominator, C naught will become smaller, okay. So you will get a very small peak. Now let us look at the chromatographic column like a stirred tank reactor. Originally you assume a single stirred tank reactor and try to model the chromatographic column, but that is a very approximate model. Then we are extending it to n stage system where n is very large. If n is very large, then the relationship becomes much more uniform or normally distributed or Gaussian distributed curve, okay. Now let us look at another approach where you are trying to model the chromatographic column like two stirred tanks. So you have a stirred tank of volume V and there is another tank, but the feed is entering this first tank and the product is going out from the first tank only, but there is a mass transfer or there is a flow of solute in and out the first and the second tank, they are connected like this, okay. So the feed is entering only the first tank and the product is going out only from the first tank, and the volumetric flow rate of the feed is Q. There is a mass transfer coefficient which relates the amount of solute in and out of the tank 1 and tank 2. So in the tank 2 does not have any in or out streams, okay. Now assume this type of system. Imagine you are giving a pulse of C naught initial concentration injected at time equal to 0. Suppose if K equal to 0, that means there is no in and out. Can you derive an equation for the concentration of this pulse as a function of time? So there is no mass transfer taking place, K equal to 0. So that means this stirred tank is completely cut off from this stirred tank. Now we are injecting a pulse at time equal to 0, initial concentration of the pulse is C naught. Can you find out an equation which relates the concentration leaving the tank 1 as a function of time? So it is very straightforward, we have to do a mass balance, input minus output equal to accumulation. So because there is no reaction, we always say input minus output equal to accumulation. If there is a reaction, then obviously there is going to be loss because of reaction. Now what is input? Whatever is coming in of the solute in the feed. What is output? Whatever is going out of the solute. Now there is no interaction between tank 1 and 2, so we do not have to consider that, and that is equal to accumulation. So input will be equal to, it is 0 because there is no solute entering. We have just injected some solute of concentration C naught at time equal to 0, that is all. After that there is no solute entering, so please remember that, that is why input is equal to 0. But there is going to be some solute leaving the tank because you have injected some solute of concentration C naught at time equal to 0. So obviously the output will be the present, but input will be 0. So output will be Q is the volumetric flow rate, C is your concentration. Now this is equal to accumulation. What is accumulation? V dC by dt. So it is a first order differential equation. At t equal to 0 we are injecting some solute, okay. So at t equal to 0 C will be equal to C naught. So if you integrate this and substitute these, you will end up with C by C naught equal to exponent of minus Q into T divided by V. So C is the concentration of the solute that is leaving the tank, C naught is the concentration of the solute that was injected at time equal to 0, that is equal to exponent of minus Q. Q is the volumetric flow rate of the solvent that is flowing in, T is the time divided by V is the volume. So how will this equation look like? it will be exponentially falling like this, okay. So initially it will start from C naught at time equal to 0 here, and then as time progresses this will keep falling in an exponential fashion, okay. Now this V volume divided by Q, the flow rate, is called the residence time of the tank, okay. V by Q is the residence time of the tank. So you see that C by C naught equal to exponent minus T by residence time. So the residence time has a very important effect on the way this particular concentration keeps falling as a function of time, okay. So we had this particular problem where we have two tanks, the tank 1 there is solvent flowing in all the time, solvent is coming out, at time equal to 0 you are injecting a solute of concentration C naught, and the mass transfer between tank 1 and tank 2 if you neglect, that means you assume the mass transfer coefficient to be 0, and we are asked to derive a relationship for the concentration of the solute leaving tank 1 as a function of time, and this is the particular relationship. It is a first order process because here you have the first order process, so a solution for the first order process will always look like this. So it has got a E exponent minus Q is the flow rate, T is the time divided by V the volume of the tank, so it is going to fall down exponentially. It is quite straightforward. Now let us look at a slight modification to this problem. So again we have the same 2 stir tank, V, and this tank is V dash. Now the solvent is flowing at a flow rate Q, and then solvent is coming out at its flow rate again at Q. There is an exchange of material because of mass transfer coefficient K, okay, and there is no streams entering this second tank, or there are no streams leaving the second tank. Now again a pulse of C naught is injected at time equal to 0. Now assume K equal to infinity, okay, that means there is complete mass transfer from tank 1 to tank 2, there is no resistance to mass transfer. Can you derive an equation for the concentration of the solute leaving this tank, first tank, as a function of time? So the problem here is different from the problem before. In the previous problem we assumed K equal to 0, that means tank 2 is not contributing anything, but in this second problem we are assuming K equal to infinity mass transfer, that means there is a complete exchange, there is no resistance at all for material to get transferred from stage 1 to 2 or tank 1 to 2 or tank 2 to 1. Now again we go back, we take input minus output equal to accumulation, and again we say when you do that we will end up with an equation like this: C by C naught equal to exponent of minus Qt divided by V plus V dash. Please note in the previous problem we had C by C naught equal to exponent of minus Qt by V, whereas here because there is absolutely no mass transfer resistance we can assume this whole 2 tanks into one single tank of volume V plus V dash. So basically in this problem we are assuming that the tank has a volume of V plus V dash, that is all. C by C naught equal to exponent of minus Qt by V plus V dash. So in the second problem, because V plus V dash is greater than V, we can see that the residence time of this system is much larger than the residence time of the first system, okay. So if you look at both the problems together, in the first case when K equal to 0 the concentration of the solute leaving the tank will be like this, because the second tank is not contributing anything, whereas in the second case when the mass transfer coefficient is infinity we are clubbing or combining both the tanks, so it is like a combined volume of V plus V dash. So the concentration of the solute as a function of time leaving the system will be like this, okay. So in reality if we have some value for k, that means if there is some mass transfer coefficient value which may be between 0 to infinity, then the performance of such a system will lie between these two extremes. So we have two extremes. Extreme 1 is when the mass transfer coefficient is 0, that means tank 2 is not contributing at all. In the second case extreme, we assume the mass transfer coefficient is infinity, that is it is almost like a telescoping or combining both the tanks V and V dash together. So it is like one single tank of volume V plus V dash. So that is how the performance will look like in case 2, this is how the performance will look like in case 1. So in any realistic system where k has a value neither 0 or infinity but something more reasonable, then the performance will fall within these two extremes. So we are looking at different types of assumptions for the chromatographic column. Okay, now let us go further. Imagine I have a 100 liter packed column, it has got a void fraction of 0.3, equilibrium constant is k is equal to 13. What is the volume at which the elution takes place? Okay, so what is the elution volume? So how long should I keep collecting until the maximum of the peak appears? So again we use one of those equations, okay, the equation where we have T naught equal to epsilon plus 1 minus epsilon k V by Q. So when I take Q together with T naught, we will get this elution volume, right. This is elution time. When I multiply this with Q, that is the flow rate, I get Q to T naught, that is the elution volume. Now I know epsilon which is 0.3, I know K which is 13, I know V which is 100 liter. So I just substitute and calculate the elution volume, very straightforward, that is equal to 940 liters. So it means that I have to collect 940 liters of the solution and then the peak will appear here. Okay. Now let us look at another problem where we are going to make use of a concept like yield. So very long time back I introduced something called yield, where if you collect a component between certain times, say time equal to t dash and time equal to t, then we can find out what will be the yield of that particular solute which we have collected. Okay, so that is what we want to calculate here in this particular problem. Okay, so you have a chromatographic peak like this. At 170th minute the concentration is 0.0063 units. At 190th minute, that is where the maximum occurs, that is the retention time, we have the concentration at 0.0152 units. What is the yield at 200th minute? That is on the other side after this. Suppose if I collect so much of component that is beyond 190 minute up to 200 minute, what is the yield? So what equation do I use? You have to go back. Now you know C is equal to C naught exponent minus T by T naught minus 1 whole square divided by 2 sigma square, right. So here I know T naught is 190 and C naught is this. From there I should be able to calculate this particular term called the sigma. Then I can use this for calculating the yield at 200th minute. Okay. So I come back again, same equation, C is given as if you go back at 170th minute C is 0.0063, C naught is 0.0152, right. So C naught is 0.0152, C is 0.0063, T is 170 minutes, T naught is 190 minutes. So I can substitute all these terms and I will calculate the sigma. So I substitute C is 0.0063, C naught is 0.0152, that will be equal to e power minus T is 174, T naught is equal to 190. So by doing all this the only unknown here is sigma. So from there I can calculate sigma as 0.063. Okay, please remember the standard deviation is sigma into T naught, that is the retention time. Okay, anyway, once I calculate sigma, I can calculate the yield by using some other equation. I introduced the concept of yield long time back, several classes back. Okay, now yield is given by half multiplied by 1 plus error function. ERF is something called error function, T by T naught minus 1 divided by square root of 2 into sigma. Okay, why does this come? This comes because we are collecting beyond the maximum. Okay, that means the yield, if you are collecting up to this, it is 0.5, and whatever is collected beyond is beyond 0.5. Okay, because we assume this particular curve to be uniformly distributed. So if I collect up to 190 minutes, the yield will be 50% or 0.5, and if I collect beyond 190 minutes, it will be 0.5 plus other term. So the equation for the yield is given by half into 1 plus error function of T by T naught minus 1 divided by square root of 2 sigma. Okay, now I know sigma, T is 200 minutes, T naught is 190 minutes, so I can substitute, and then if I know how to calculate error function, I will be able to calculate yield. So it is very straightforward. So here T naught is 190, T is 200 because I want to calculate the yield at 200 after 200 minutes. Sigma is given here 0.063, so I just substitute and I just have to calculate the error function, that will give me the yield. Now let us look at how to calculate error function. Okay, how to calculate error function. Okay, straightforward. Error function is a number which can be calculated using certain numerical technique. Okay, error function is defined like this: error function of x is equal to 2 by square root of pi 0 to x e power minus t square dt, and error function looks like this. So as x varies like this, error function looks like this. So it is very low, that is -1, and it rises sharply, it is like a sigmoidal curve, and then after some value of x it reaches 1 and it remains constant. So the error function, that is the left hand side, varies between -1 to +1, okay, like this. When we move the x, that is whatever the term inside the parenthesis, when we move from a negative value to the positive value. Okay, so if we consider only positive range for x, that means x varying from 0, 1, 2, 3 and so on. So error function of this particular x will start from 0, it will rise and then it will saturate at the value of 1. Okay, so the error function x is given by 2 divided by square root of pi integral 0 to x e power minus t square dt. So for different values of x, there is a table which gives the corresponding value of the y, that is the error function of x. In fact, this is what it is. So for different values of x, the erf x, that is whatever is there on the left hand side, is given in the form of a table. So we can get erf x when I know x. So when x is equal to 0, error function x is equal to 0 as well. As the x goes up, this also rises sharply and then it flattens out. So you see after some time it is practically 1 because there is a saturation, then it does not cross 1, so it reaches the saturation value of 1. So initially it starts from 0 and then it rises sharply, then after that you can see that it is flattening out and it will never cross 1. So after about 1.7 or 1.8 we can practically assume, so if the x is above 1.8 or 1.9 and so on, we can practically assume error function of that is almost equal to 1. So that this particular table we are going to use in our problem to calculate the yield. Okay. So we take this equation again, and we know T which is 200, and we know T naught which is 190, we know sigma which is 0.063. So we substitute here, so we will get some value for the x. Once I know the x, I can use the table and I calculate error x, which I substitute here, and then yield will be equal to 0.5 multiplied by 1 plus that particular value. Okay. So when I do that, I end up as yield equal to 80%. So the yield up to the 190th minute, that is where the retention time or the maximum happens, the yield will be 0.5, and when I go beyond the 190th minute, the yield will be much more than 0.5, which is given by this extra term here. So Rf x is equal to T by T naught minus 1 divided by square root of 2 sigma. So you calculate the x, and then from the table you calculate the Rf and then substitute here, and this side is 0.5 multiplied by 1 plus something, so the yield is 0.8, that means 80%. So if I collect the sample up to 200th minute, I will be collecting 80% of the sample. This is not telling anything about the purity of the sample, but it is telling about the yield. So if I collect up to 190th minute, I am collecting 50% of the sample. If I am collecting up to 200th minute, I am collecting 80% of the solute or the protein or metabolite which I am trying to recover, 80% of it. So if I go up in time, I will be collecting more of that particular solute or protein. But as I said again, I am not talking about the purity. If there is another protein that is present after certain time, that protein may come out as an impurity. So generally what happens is, if my yield increases, my purity goes down, and if my yield decreases, my purity goes up. So you need to strike a balance to see if I am interested in very pure compounds, or if I am interested more in collecting as much of the product as possible. So if I may resort to some other type of purification step beyond this particular stage, I may be interested in collecting all the material. So I would like to have very high yield but low purity, and then I may resort to another type of chromatography to improve the purity. Whereas if I am interested in the purity of the compound, that means like a pharmaceutical protein or something, then I will see to that there is no other protein coming during my collection stage. In that process I may lose lot of this particular desired product in the effluent stream. So my yield may go down considerably. So you need to decide, do you want to have all the protein or as much of the protein collected with poor purity, or do you want to collect very pure product? That means the problem will be poor yield. So if you want to do that sort of calculations, we can use these equations to do that sort of calculation. So the main equation that comes here is yield is equal to 0.5 multiplied by 1 plus error f T divided by T naught minus 1 divided by square root of 2 into sigma. So T naught is your retention time, and T is the time up to which you are collecting your sample. Sigma you calculate from the previous data which is available. Sigma T naught is the standard deviation of the Gaussian distribution. Okay, let us go forward and see how to analyze this type of problems much more stringently. Now we are trying to make this problem more complicated. Now we have two different proteins, and that is eluting out of a chromatography. Okay. So this is protein 1, this is protein 2, we call it I, impurity. So the first protein has an elution time of 6.42 hours, the second protein has elution time of 7.6 hours. Okay. At 6.42 hours, protein 1 is 82% and there is no protein 2 or the impurity, so it is 0. At 7th hour, protein 1 is 63%, protein 2 is 0.14%. At 7.6th hour, protein 2, that is the impurity, is 43%, protein 1 is 28%. Typical example. Okay. Now we can make use of these equations, right. By making use of this equation, what can we calculate? We can calculate sigma for protein, we can calculate sigma for impurity, correct. So we can use these equation, we can calculate sigma for the protein because we know the T naught for the protein, which is 6.42 hours. Okay. We know the T naught for the impurity, which is 7.6 hours, and by using these two T naughts, we can calculate corresponding sigmas for protein as well as for the impurity. That is what we are going to do now. Now we want to calculate the yield. So if I am collecting sample between time t dash to t, where T naught is the retention time of the component, then yield is given by half into error function T by T naught minus 1 divided by square root of 2 sigma minus error function T dash by T naught minus 1 divided by square root of 2 sigma. Okay. Now the purity of any solute, as I mentioned, now you have many components. In the previous example we are having two components. So it is given by concentration into yield of component 1 divided by concentration and yield of component 1 plus concentration and yield of component 2. So the purity of the solute in any collection pot will be how much of concentration and yield of component 1 and component 2 are present. So if there are n components, obviously in the denominator we are going to have a summation of all these components. So if yield increases, purity will go down. As I said, if yield decreases, purity will go up. So if you want a very pure material, your yield is going to be sacrificed. So we can, in the previous problem, you can calculate sigma for the protein, we can calculate sigma for the impurity, and then we can use this equation to calculate the yield, and we can use this equation to calculate the yield of the protein, we can use this equation to calculate the yield of the impurity if I am collecting a sample between T dash and T. Okay. So once I know the yield of the protein and once I know the yield of the impurity, I can use this particular equation, okay, and then calculate what will be the purity of the protein in the sample I have collected, what is the purity of the impurity that is present in the sample. So it is a very interesting problem. This is a realistic situation where we have two proteins, but in reality there might be many proteins, especially if you are talking about human sample and then I am trying to purify one particular protein from mixtures of protein, then you may be having 10, 20, 30 different proteins, and separations of those proteins are going to be a challenge. So the purity always is going to be a real challenge. So here the factors which govern the protein purification depends upon the interaction between the protein and the stationary phase. And what are the factors which we observe? We observe something called the T naught, that is the retention time, and we observe something called the sigma, okay, where T naught sigma is the standard deviation of that particular curve or the concentration leaving the column. So it is very specific to one particular system or one particular solute. So T naught will be different for protein 1, T naught will be different for protein 2, similarly sigma will be different for protein 1 and sigma will be different for protein 2. So by looking at various times at which these two waves travel out of the column, we can calculate the sigma, and then once we know the sigma for the protein and the impurity, we can calculate the yield of the protein, we can calculate the yield of the impurity. So we see we have used a lot of equations, very simple equations. The most important point is looking at the purities, looking at the yields, and we also introduced a new terminology called error function x, where error function is integral which has certain limits, and this error function x varies between 0 to 1, afterwards there is no increase. So it is like a saturation type of curve. So there are tables available which gives you the value of error function x for a given x. So if I know the x, immediately I can calculate error fx, then I can substitute here. So if I know the value of x, I can calculate fx and I can substitute here, I can calculate the yield. Okay. Now we have looked at many things. We have looked at a discrete stage modeling of a chromatographic column, that means multiple stages. We have looked at a single stage modeling, we have looked at two stages connected with mass transport, and so on. Now let us look at another approach, that is called the continuous packed bed model. So we assume there is a continuous packed bed and the solution is flowing along the z axis, that means it is flowing in the z axis from left to right. The solute is carried because of the solvent flow, okay, number 1. Solute moves because of diffusion or dispersion. Solute gets accumulated in the voids or interstices of the bed. There are voids, so there are solution entrapped in the voids, so some solute is there. Solute is accumulating in the stationary matrix, that is the stationary phase, because of adsorption or partition or interaction between the stationary and the mobile phase. So many things are happening. So this is a continuous packed bed model. The solute is moving from left to right along the z axis, and so the solute is carried because of solvent flow, solute is carried because of diffusion along the axis of the tubular bed or dispersion, solute gets accumulated in the voids or interstices of the bed, and the solute is also present adsorbed onto the stationary matrix. Okay. So all these things happen. So if all these things happen, we can still write some partial differential equations which describes this particular type of phenomena, and this is how it is given. It looks very complicated, but each term has certain particular significance. Now this term, where we say d square c by dz square into capital D, is arising because of diffusion or dispersion of the solute along the axis. This term V into dc by dz is arising because of the movement of the solvent. V is the velocity, superficial velocity of the solvent, C is the concentration of the solute, Z is the bed. So concentration of the solute along the packed bed, okay. So this term arises because of the diffusion of the solute in the column, this term arises because of the movement of the solvent, and on this left hand side we have all the accumulation term. We have C is the concentration of the solute in the mobile phase, so epsilon is the voidage, bed porosity, and 1 minus epsilon is the amount of stationary phase, and dq by dt, where q is the concentration of the solute which is bound to the stationary material. So this left hand side is all related to accumulation, right hand side has two terms, one related to the diffusion or the dispersion of the solute along the bed axis, other one comes because of the movement of the solvent, and this is how we end up with a partial differential equation. We have z, that is the axis of the column, so there is going to be concentration variation along the axis of the column, there is going to be concentration as a function of time as well, that is why we have T coming here. Now C is the concentration of the solute in the mobile phase, Q is the concentration of the solute that is in the stationary phase, that is adsorbed on the stationary phase. So if we have a very simple relation between C and Q in a linear fashion, then we can combine them together nicely without any problem, like we did that in the previous case. For example, Q can be equal to Kc or something like that. Okay, now let us continue this problem, this particular continuous packed bed model in the next class.